All right, so the other day I started out with this particular circuit here, all right, where you're looking at essentially what I call an LRC series circuit, right? There's an inductor, a resistor, and a capacitor in series with each other. And basically you're closing the switch at t equal to 0, and we were solving for the capacitor voltage. All right, so we did an example like this on Wednesday last week too. The big difference here is that my R value is a lot bigger than it was before. So if my R value is a lot bigger, what's that mean about the losses in this circuit? There's going to be greater losses, right? And I know that because the I squared R values are going to be higher. So basically, what we did last time is I basically got through the first two steps, right? And I have in here what my steps are, right? So step one is to get the differential equation. Step two is to solve for the differential equation. And when I say solve for it, basically just get the general form of it. All right. So we went through this, like I said, we went through this last time. I'm not going to discuss this, too much further, other than to say what we did was we wrote down the differential equation. You can go back and watch the video if you don't remember, right? We basically ended up with this differential equation for the capacitor voltage. And how from there do we determine whether this thing is underdamped, overdamped, critically damped? What's the procedure? So I got this last step. The bottom thing here says 24 over LC equals whatever, d squared BC dt squared plus R over L times blah, 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 blah. How do I determine whether that is this differential equation right there? How do I determine whether or not that thing is underdamped, overdamped, critically damped?
Find alpha and omega.
I got to figure out the alpha and omega, right? So basically what we do is we have this very general form that I gave, right? Basically where I look at the roots of my characteristic equation, right? And the characteristic equation comes from solving the homogeneous solution to that thing, where you guess A equals, or you guess the solution is A e to the st, okay? And you change, instead of this thing, how does that turn into a homogeneous equation? Who remembers that? What I actually have to do? That's the differential equation, has that form. The transient solution solves this if I set it equal to 0 instead of whatever it's actually equal to, right? That gives us this characteristic equation. We solve for that. The two roots are in terms of that thing. So what we said is this guy, the solution to this thing in general, the transient solution to this guy, or really the total solution, is always equal to whatever the steady state value is, plus A1 e to the S1t plus A2 e to the S2t, like that. All right, now the question is, what are S1 and S2? All right, S1 and S2 could be real or they could be complex. What makes them complex? What determines basically the nature of the solution? Looking at that, what determines the nature of the solution? Yeah, that's square root of alpha squared minus omega naught squared. That could be positive, the alpha squared minus omega naught squared, or it could be negative, right? So basically, we end up with three choices, right? And these are summarized in the notes. Basically, underdamped, critically damped, overdamped. If I get the underdamped case, this is where my exponentials, I still have exponentials, but they're, as you're seeing with Dr. Yawu, there's a relationship between cosine, sine, and the exponential function, all right? They're still exponential, but they basically turn into decaying cosine and sine functions. And in the overdamped case, it's just basically a decaying exponential. And I say decaying. What's going to be true about S1 and S2 always? What's going to be true about, and also, yeah, what's going to be true about these exponentials, the S1 and S2? They're always going to be negative. They're always going to be decaying. If they were positive, what would that mean about the transient response? It wouldn't be particularly transient, right? It would go to infinity, right? And things, in reality, if you ever had that, it would never happen. Things would explode. Your inductors would explode. Your capacitors would explode, right? Because it's telling you that the voltages and currents would become infinite, and that's not possible. Okay. All right. So what I did too is I went through and I basically in the notes came up with, all right, in each of the different cases, here's what our initial condition equations look like. So I basically took the standard form of the solution, plugged in t equal to 0. The big thing here with these second order things is I don't need just an initial condition for whatever I'm solving for, but I also need an initial condition for what? Not just for the thing I'm solving for, but what? The derivative of the thing I'm solving for. All right. So you got 3 problems on the current homework due Friday that cover second order. All right. So you got a fair bit of stuff to go over there to help yourself prepare. Okay. All right. In terms of, kind of the process, right? So we went through this the other day. I did 1 and 2. 1 and 2 were to get the general form of the solution. We determined, we're gonna go back to what we determined it to be here in a second. But then where I stopped was basically getting the steady state values, right? Then figuring out the initial condition for the quantity I was solving for, the initial condition for its derivative, and then solving for the unknowns to get the final solution, the total solution. All right, so we ended up here. Basically, I got my differential equations. I figured out what A and B were, and then I figured out what alpha was, right? So where we ended up last time is I ended up here, right? And I solved for these particular things, and I ended up with alpha being equal to, again, this is how I put it into MATLAB here. So I put in my A and my B values. And I ended up with alpha being equal to, in this case, for the values of A, B, and C. So A, B, and C all depend on what the resistor, inductor, capacitor are. I ended up with alpha being equal to 140,000. And I ended up with omega naught being equal to 5,000. Okay. And we said that our form of the solution is negative alpha for these roots. Like that. All right. So if I have that form for my alpha, and given the value of alpha that I have there, 140,000 and 50,000, what type of thing is that going to be? What's true about my roots there? Alpha squared minus omega naught squared. What's true about my roots for the value of alpha and omega naught that I have here? Positive. Yeah, the thing is positive, right? The thing under the radical sign is positive, right? So basically what I have is the fact that this should be, if I go back to my general types of solution, this should be overdamped, okay? So it's overdamped. So if it's overdamped, that means, just going back to that summary, when it's overdamped, alpha is bigger than omega naught, and my roots are real, okay? So I say here, there's the 2 roots are S1 and S2. So S1 for me is always the one with the plus sign, and S2 is the one with the negative sign, okay? So basically what I end up with, if I go through the math on this particular one, is I end up with, right here, oops, I'm too far. I end up with S1 equal to negative 89, and S2 equal to negative 2.799 times 10 to the 5th. All right, so they're pretty significantly different, those two. All right, but they're both real, all right, and they're both negative. We would expect them to both be negative, and they're both real because of the fact of what I have for the alpha and omega naught. Okay, all right, questions about there? All right, so then we get to the third step. All right, third step is basically find steady state values for IL of infinity and VC of infinity. Now, I'm solving for V sub C, so I don't really need I sub L, but I want to ask you guys anyway, just because you need to practice, right? So what's the circuit look like? So if I'm in steady state, what's the circuit look like? What do I do with that switch? The switch is going to be closed. Okay. So I got my 24-volt source. I got my switch closed. What do I do with RL and C? Well, R doesn't change, right? What's L do? Short, right? What's the capacitor do? Open. All right, so I have V sub C of infinity and I sub L of infinity. Yeah.
question about the previous slide. What is S1 and S2? I don't know what's going to
S1 and S2 are the roots, right? So we said there's well, they're the two roots. In other words, the two values of S that solve that characteristic equation.
solve a game when it's other than imaginary.
If it's underdamped, they're complex.
Oh,
Yeah, so they're not going to be purely imaginary because there's always going to be a real part to them. Right. If they're purely real, then yeah, it basically becomes, and I should be clear, if they're purely real and distinct, meaning there's two different numbers, that's when it's overdamped. They can be real and the same number, and that's where we have what we call critically damped. Okay. And again, that one doesn't happen as commonly, but it does happen. All right. So here, back to this problem, what is the steady state value of the current? Zero, right? Can't be any current in the circuit with an open, right? And this value here, VC of infinity, is what? 24, right? Now, how do we know that it's 24? Why isn't there any voltage across the resistor? No current, right? I times R is equal to 0 in this case. And KVL always has to be satisfied, so that better be 24 volts on that thing. All right. So step 4 basically is to figure out what is the value of VC0 plus and IL0 plus. And you find that by the fact that capacitor voltage, inductor current always have to be continuous. And I told you in this case that the initial value is 10 volts on the capacitor and 0.1 amps on the inductor. So there's really nothing that I need to do for this step, right? If I knew what the values were before the switch, how they got to be that value, I don't know. I just told you what they were. All right. All right. The step 5 is basically where I have to find for myself what is the initial condition on the derivative. Now, I'm solving in this particular case for V sub C. So the only one I really need is this. All right. Now I'm going to solve for both of them though, right? Because it kind of matters to me. So what am I doing? What does the 0 plus mean about the conditions in this circuit that I should draw? The switch should be closed. Okay. The switch should be closed. Now, the tricky thing here is we said inductor current always has to be continuous. Capacitor voltage always has to be continuous. And we're looking at a really short time from 0 minus to 0 plus. This could be 10 nanoseconds of time that I'm talking about. If the capacitor voltage is continuous over that short period of time, doesn't change, and the inductor current is continuous and doesn't change, how do we model those two things during this really short time period? Yeah, so we say that the inductor is like a current source that is carrying 0.1 amps, okay? And we say that the capacitor is like a voltage source that is carrying 10 volts. And just to be clear, this value is VC0 plus, the voltage there, which is going to be 10. And this is IL of 0 plus. Now, what I'm interested in is the derivatives, right? So how do I get the derivatives? What do I know about dV/dt? That's the thing I'm really most interested in here. dV/dt. So what's that related to? What can I solve for in the circuit to give me that? I see, right? Because I have C dV dt is equal to I sub C. So what I really want to find out is what is the inductor, or what's the capacitor current at this time? All right. So what is it? I know what it is without doing any work. 0.1. How do I know it's 0.1? Because I have a current source here. Current source is basically locked in the current at a particular value. So without doing any analysis, I know that I sub C of 0 plus is equal to 0.1 amps. Okay. And that's got to be equal to C times dVc dt of 0 plus. All right. Now, I know what C is in this particular problem. C is equal to, I think it's 0.4. What is it? Times 10 to the minus 6. Yeah, 0.4 times 10 to the minus 6. Is that a weird number? Not really. That may sound weird to you, but 0.4 microfarads is what that is. It's pretty normal. It's actually pretty big for a capacitor. All right. So 0.4 microfarads. So that tells me that dV/dt, so this is 0.4 microfarads, or 0.4 times 10 to the minus 6. So dV/dt at 0 plus, if I do the math on that, that works out to be 2.5 times 10 to the 5th. It's a big number. And that has units of volts per second. All right, because it's telling me the rate of change of the voltage, 2.5 times 10 to the 5th volts per second. That tells me that that capacitor voltage is changing really fast initially. All right, that's basically what it comes down to. All right, the capacitor voltage is continuous, but it's starting to change. Right, that's basically what we're finding. Okay. Now, I also want to do real quick the inductor current. I don't need that to solve anything about the capacitor voltage. All right, but I want to do for the inductor current the same thing. What's the rate of change on dIL by dt? So how would I do that? All right, so we got the same circuit. All right, I've got 24 volts. Got my R. This guy's become 0.1 amps. This guy is 10 volts. Okay. All right. I'm interested in solving for this guy, dIL by dt at 0 plus. Okay, so to solve for that, what do I need to solve for? Inductor voltage, right? Now, the inductor voltage I defined back at the beginning of the problem to have this polarity, VL like that. Polarity matters to me. All right, so I'm going to write it as VL of 0 plus. The beginning of any problem you solve, choose a polarity for everything and don't ever change it again. All right, first step, set that at the beginning, don't ever change again. All right, what happens is you guys change halfway through, and that's when you're wrong. All right, set it at the beginning and then always come back to that. Okay. All right, so how do I solve for what that is? KVL. All right, so I basically do my KVL. I always say I always go around in a clockwise way, and I start in the bottom left corner. So I get 0 equals negative 24, because I go minus the plus on the 24 volt source. Now again, the beginning of the problem, I define the resistor to look like that, and the capacitor is defined already. So I say negative 24, and so what do I do for this resistor here? How do I write that? Plus, and how would I write it specifically? Well, it's 0.1 times whatever my R is. If I go back to what I defined it to be, that R is 28,000, 28 kilo ohms. Okay. And then what do I do when I get to the inductor? Yeah, it's just VL, because I don't know what that is. I never know what the voltage across a current source is. That's defined by the circuit itself, right? And then I have 10 volts on the 10 volt source. Okay. So here's the tricky part. 0.1 times 28,000. That's the voltage across the resistor. What number is that? 2,800. That's a big number, isn't it? Especially because it suddenly appears across that resistor, right? I have almost 3,000 volts suddenly appearing across that resistor at t equal to 0. Right? That is, in fact, what would happen. That's what, when you look at these circuits, that is what happens in these sorts of circuits. You get huge voltages and currents and things like that that develop all of a sudden, simply to keep the physics satisfied, right? Simply keeping the inductor current continuous and the capacitor voltage continuous. The resistor, everything else is just going to react however it has to react to make sure those things stay true. All right. So if I solve for this VL of 0 plus, I end up with a crazy number here. Basically putting all that stuff in there, I end up with, what did I get? Negative 2,786 volts. All right. That would be the value that I would come up with in going through this whole thing. Okay. And then what do I have to do? I then have to figure out what dIL by dt is, right? So dIL by dt at 0 plus is just whatever that voltage is divided by L. right? That just comes from the fact that LD IDT is VL, right? So what's that going to be? Even bigger, right? That's going to be 27,860 because the value of L is 0.1. Okay. But again, we don't need that to solve the problem. All I needed was actually what I solved for before, which was the capacitor voltage thing. Questions about what I did there? Okay. All right. So, all right, we'll keep going. All right. My last step is to use my initial conditions to find the unknowns in my solution. All right. So what I do is because this guy is underdamped, right? What I had was that, let me do it specifically for the capacitor voltage. I have that it's V sub C of infinity plus A1 e to the S1t plus A2 e to the S2t. And I had that S1 was negative 89 and S2 is equal to, what did I say, negative 2.799 times 10 to the 5th. Okay. All right. Now to get the initial condition, I know what V sub C of 0 was, right? V sub C of 0 is equal to 10 volts. What's that equal to in terms of this guy right here? What do I do if I want to solve for A1 and A2? Well, I can plug in T equal to 0 into that whole thing, right? If I plug in T equal to 0 to this equation, what do I get? Yeah, so I get V sub C of infinity plus A1 plus A2. And V sub C of infinity we solved for was 24 volts. All right. So at this point, I can't solve for either A1 or A2, but I know that A1 plus A2 is equal to negative 14. All right. So I've got that part. Now, what was the other thing we needed? To get both A1 and A2, I need another initial condition value, right? What do I need? There's a whole reason for doing that last step 5, right? What do I need? You guys awake at all? The derivative, right? I need the derivative, right? That's the whole reason why we went through that last step, was to get the derivative, right? Now, I guess I've got the solution to that, but just to be clear, right? That means I need dVc dt, right? That means take the derivative of this guy, right? And we have a number for this whole thing. So dVc dt, the number that we had was 2.5 times 10 to the 5th. Okay. Now, if I take the derivative of this guy, what do I get here? Well, it's not that ugly, right? It actually turns out to be not too bad, right? What's the derivative of Vc of infinity? That's a constant number, right? That's 0. The derivative of A e to the S1t is S1 A1 e to the S1t, right? The S1 just comes down. And then for the other one, it's S2 times A2 e to the S2t. Now, because I specifically am looking at this at t equal to 0, what's true about e to the S1t and e to the S2t? What's true about those things at t equal to 0? Just 1, right? So each of these guys is 1. So that tells me this whole thing is S1 A1 plus S2 A2. All right. Now that's what I have in my summary slides. Is I basically have this stuff here. All right. Where I basically said for you, well, at t equal to 0, it always has this particular shape. The thing that you guys will screw up when you start doing this stuff is you'll match A1. You need to make sure that A1 and S1 actually match up with each other, and A2 and S2 match up with each other. You don't reverse them, right? As long as you don't do that, those formulas work just fine. Okay, and you can go back to those. So what I do in this particular case is I have, all right, we just solved this. I ended up with negative 14 equals A1 plus A2. And I had 2.5 times 10 to the 5th equals S1 A1 plus S2 A2. I got 2 equations and 2 unknowns. You can do that however you want. All right. What I said is I like to do that with MATLAB. So how would I set that up in MATLAB? Yeah, I'd make a matrix here. So this guy, I'd have negative 14 over here, and this would be 2.5 times 10 to the 5th. And how do I set up the rest of that problem? What am I solving for again? A1 and A2. S1 and S2 are numbers that I know the value of. So what would go in the matrix there? What's the top row? 1 and 1, right? Because negative 14 equals 1 times A1 plus 1 times A2. And then I'd have S1 and S2 on the bottom. Okay. Now the way I enter that in is like this in my code. And I've got my code in the last slide, right? Basically what I do is I put in here. So if you look at what I had here, I called this right here Y. I called this CX. And I called this A, I guess. Okay. And what I did was I left this, I guess, in terms of variables, but if you look at my numbers, this is the negative 14 and DVC is the 2.5 times 10 to the 5th. Okay. And I end up getting those A values by doing inverse of CX times Y, right? And the numbers I ended up with here, I got that A1 was equal to negative 13.11 and that A2 is equal to negative 0.889. Like that. All right. Now, again, I've got my code here, so you can look at it too. You can work from that code when you try to do your stuff in MATLAB if you want to. Now, what the heck should this thing look like? All right, before I look at the graph of it, I want you guys to tell me what the heck it's supposed to look like. All right, it's going to be an exponential. All right. And if it's overdamped, what does an overdamped solution look like? It's a decaying exponential. Well, it's a decaying exponential. Let's say it that way. I don't know whether it's fast or slow. All right. It's a decaying exponential, which is a little bit weird here. Where's it going to start and where's it going to end? It should start at the initial condition and should end at the final condition. Okay. So it does that. Starts at 10, ends at 24. Now, you guys may be asking, well, it doesn't look like it decayed, right? It actually looks like it increased. It did decay in the sense that what it is right, if I look at the solution, it's V sub C of t is equal to 24 volts, the final value, plus A1 e to the S1t plus A2 e to the S2t. That's what you have graphed right here. So the key thing is people say it decays. Well, what is it? That's the thing we got to be careful of here. Something decayed. The total solution did not decay, right? The total solution went from its initial value to its final value, just like it should. What decayed? Okay. The transient solution went to 0. This guy here is the transient solution. As t goes to infinity, what's true about A e to the st? If s is a negative number, and I said s is always going to be a negative number, what's true about the transient solution? Always going, in the limit as t goes to infinity, those exponentials are always going to do what? Go to 0, right? Which they did. All right, and that got my final solution up here to the value that we got it to. Okay. All right. Now, one thing that's goofy is how many exponentials are in this thing? 2. It kind of looks like 1, doesn't it? All right. Now, it is always weird. The way these guys behave is always kind of tricky because it depends on what the relative values are. One thing you'll notice about real quick is if I were to actually zoom in on that section, right, it actually is doing something pretty goofy there at the beginning, right? And if I zoom in on it, that's actually what it looks like a little bit more zoomed in. You see it making a sharp change and then a gradual change. Any idea why that would be? It's not the kind of question I'm likely to ask you on a test, but what intuitively, why would that be that one of these, so why would it change sharply and then become gradual? Well, it's related to the fact that it's overdamped. Basically, this guy's two exponentials. One of them decays away fast, and the other one decays slow, right? This is the one that decayed fast. And then the one that takes a long time to decay is what's causing that gradual change. All right. So again, that's not necessarily something I would ask about on a test, but again, what I have here is two exponentials added together. One is decaying fast, one is decaying slow. All right. Zoomed out on a wide time scale, I can't even see basically the effect of one of the two of them. If you asked me, you just showed me that picture, I would say, well, that looks like it's probably first order, right? And so it looks like what I would see for a first order system. Okay. All right. Now, if you want to go back and see how I generated all those graphs, super tiny, too hard. Well, it's actually not too bad to read here. But if you can look at what I posted online, and you can try to run that code to try to play around with that. Okay. All right. Questions about that example? All right. We're going to keep doing examples. So basically what we're going to do is I'm going to do, this is today's notes. All right. So if you're following along on the Canvas stuff, this is the 9-6 before stuff. So we're going to do, as it's called, another second order example, right? And I'm going to do another one on Friday in recitation, or sorry, in lecture. All right. Yeah. So, and that's probably going to be just about the end of second order, the end of this week, right? There's going to be lots of these examples, and then we're going to move into the next topic, which is really AC circuits. Okay. All right. So the same basic stuff, but here's my circuit. All right. So this is pretty similar. If you've done your homework, this is the same circuit that you have in problem 3 on the homework, except in problem 3 on the homework, I ask you to solve for the voltage here, V, across this thing, so the capacitor voltage. In this case, I'm asking you to solve for the inductor current. Okay, it can be similar but different. All right, and I'm told that what the C value is 25 nanofarads, the L value is 25 millihenries, and the R value is 400. So real quick, millihenries, you're probably used to milli, right? What's nanofarads? 10 to the negative 9. So this guy is 25 times 10 to the minus 9 farads. Again, for a circuit built on a circuit board or the breadboard, that's a pretty normal value. Okay. All right. So if I want to go through my steps to solve this, what's the first step? What's the first step? Well, let's go back. Well, my first step is actually to get the differential equation. All right, that's the one I'm calling. So I want to get my differential equation for I sub L. All right, so how do I go about doing that in this particular case? Any thoughts on where I start? KCL. Yeah, KCL is a good place to start. And at t equal to 0, I am opening up the switch for myself. And I want to pretend like those numbers don't exist for a second. Yeah, pretend like those numbers don't exist. All right. I want to find my differential equation for I sub L of t. So how do I approach this? So it's for t greater than 0. So what do I do with that switch? Open it. Okay. So I got my capacitor. I got my inductor. And I got my resistor. And I'm solving for the voltage. Here, at least that's what I'm doing in the homework. In this particular case, I'm interested in I sub L. All right, so if I do KCL, in terms of the way these currents are defined, I have IC, IL, and IR. All right, again, I want to pick polarities for everything. Here's VC, here's VL, here's VR. Everything's defined like that for me. And I said IC is going down, IL is going down, IR is going down. Okay, so KCL is what? Right. The way I write this is I say it's the sum of the currents into the node equals the sum of the currents out of the node. So what's the sum of the currents into the node? And what node am I talking about? I'm talking about this one right here. Right? How much current's going into that top node? I, which is 24 milliamps. Okay. 24 milliamps is into that top node. How much is coming out? Yep, it's the sum of IC plus IL plus IR. Okay. All right, so I have I equals IC plus IL plus IR, and I'm interested ultimately in a differential equation for IL. So that means I need a second derivative of IL and a first derivative of IL. Okay, so what do I do next? Well, I got to get the differential equation in terms of IL. So yeah, what are my tools here? So I sub R is what? I sub R is equal to the voltage divided by R. How's that help me at all? Let's remember the other tools I need to remember. So VL equals LdIL by dt. And V sub C, or sorry, I sub C is what? C dV C dt. Okay. All right. So knowing that, how can that help me at all with I sub R? The voltages are the same, right? The voltages, so if I look at that circuit, the voltage across the L, voltage across the R, voltage across the C are the same. How do I know that? Because they're all in parallel with each other. All right, they're all in parallel with each other. So if that's true, help me out then. Probably helps for me to write this like this. I sub R is equal to V sub L over R, right? How can that help me turn this guy, this KCL, into a differential equation?
Into IL equal to I minus IC minus IR, and then plug in
I don't want to get IL by itself. All right. I want to get a differential equation. I see where you're going with that, but my goal is to get a differential equation. So I want to focus on this guy. So IR equals VL over R. How do these guys help me to get this into a differential equation? Substitute what here? VL, right? I can use this. So if I plug VL into that top equation there, I get VL is L over R DIL by dt. Now that I plug back into my original KCL. So it's now starting to look more like a differential equation, right? So I say this guy is I sub C plus I sub L plus L over R times DIL by dt. All right, so I'm making progress. But what do I also need? I need a second derivative in here somewhere, probably. So I sub C. Well, I sub C, I can plug in here. I know that that's C dV dt, right? And I said it was C the capacitor voltage by dt. But what's true about the capacitor voltage and the inductor voltage in this circuit? Same. They're the same. If I look at this circuit, if I do a KVL around there, voltage on the inductor, voltage on the capacitor are the same. So this guy becomes C dVL by dt, right? I wrote it, I basically took this bottom thing and I wrote it in terms of VL because VL and VC are the same, plus IL plus L over R DIL by dt. Now, that's a differential equation, yes. But I need a differential equation that's all in terms of one variable. And I want it to be all in terms of I sub L. So what do I got to do next? What do I plug in? So it's that first term, this guy here, he's the one that's the problem for me, right? He's not an I sub L yet. How do I get that to have an I sub L in it? V equals L di dt, right? I plug that into the V sub L and that becomes a second derivative. And this guy becomes LC times d squared IL by dt squared, right? Because I take the first derivative of a first derivative, that becomes the second derivative. Plus, I'm going to rearrange a little bit here, L over R times DIL by dt plus I sub L. Now, you guys, if you haven't thought about this, you haven't started the homework, then you may not know this, but is that in my standard form? No, to get that to my standard form, I gotta, what's supposed to be true to get to the standard form that I gave in the slides?
Coefficient of that.
Coefficient of the first term should be 1, right? So yeah, so basically I should divide both sides of this equation by LC, right? So I should end up with I over LC equals D squared IL by DT squared plus what? Plus 1 over RC DIL by DT plus 1 over LC times IL. Now, in my terms, I call this A, I call this B, right? I've got my differential equation, okay? And I go to my step 2, which I'm not going to solve right now, all right? Because that's, to me, that's just a math step. Step 2 is basically, all right, I got to look to see if this guy's overdamped or underdamped. I have S equals negative alpha plus or minus the square root of alpha squared minus omega naught squared. And if I look up the values here, A is equal to, so alpha is what? 1 away from it. Alpha is A over 2 and omega naught's the square root of B. Okay. Alpha is A over 2, omega naught is the square root of B. I plug that all in. Turns out I'm going to find out this guy is overdamped again. Okay. Overdamped was the same kind of one that we just did. Okay. What I want to do in the time that I have left, okay, is I want to look at the final and initial conditions real quick. All right. So here's our circuit. My third step here, step 3, is to get for myself the initial conditions. Try the final condition. All right. And the thing I care about is IL of infinity. All right. So my final condition, what's this guy look like? At t equal to infinity, what's true about all the stuff in this circuit? All right. I have this current source here. T equal to infinity. What's true about the switch? Switch is open, right? Because we're opening that switch at t equal to 0. What's true about the capacitor? It's an open. What's true about the inductor? It's a short. What's true about the resistor? It's a resistor. Okay. So what do I know? Here's I sub L. I sub L of infinity, the final value is what? I. Which works out to be, for the numbers I gave you, 24 milliamps. All right. In other words, all the current from that current source is going to go through that short circuit, basically. All that's going through the inductor. Now, step 4 for myself, what I want to do in step 4 is I want to solve for the initial conditions. All right, so I'm going to real quick. So I want to actually solve for the initial conditions here too. All right. So how would I solve for the initial conditions? And so in this case, I'm talking about, I want to get IL of 0 minus. IL is 0 minus. How would I deal with that? So, yeah, I've got this inductor. What would the switch be doing? The switch would be closed. The capacitor is here. What do I do with the rest of the circuit? Well, the inductor is a short too. And then I got the resistor here. Now this is a situation, which is why I gave a number, right? Because I got 2 short circuits in parallel. What's the current in each one? To be perfectly honest with you, I don't really know what the answer to that question is. Ideally, it would be half, but we're dealing with a weird situation here, right? In reality, what would happen is there'd be a little bit of resistance in both of those paths. And there'd be a tiny, tiny little resistance. And based on how much resistance was in each path, the current divider would tell me how much current went down each one. Okay. One thing we can tell for sure is what's V sub C of 0 minus? 0. All right. Why do I know that? I got a short circuit. All right. I definitely got that situation going on for me. Right. This is why I gave a number, because it's a little bit unclear. Right. The assumption would be I wouldn't give you a circuit like this where it was ambiguous, because it was during a test, my phone would light up with phone calls from you guys, right? I know that. This is a weird situation. All right. What I'm going to say is that I'm just going to tell you, that's why I had a number there at the beginning. I'm going to say that it was I over 2. Right. So 12 milliamps. Okay. Now, how would I get the last step here? Step 5. Step 5, I got to do the derivative thing. So we're going to pick up with this again Friday, but I want to draw the circuit here real quick, right? What would I do with the switch? What would I do with the switch? If I'm interested in 0 plus, what's the switch do? Switch is open. All right. What about the capacitor? We say the capacitor is set to a voltage source during this time, right?
Yes.
So a voltage source of what value? 0, which is a short circuit. So I have what? So I have the inductor is like a current source, right? And then the resistor is like a resistor. Now, this is IL of 0 minus. But basically what I have here is I have I here, and I have I over 2 here. So how much current is going through the inductor? Well, it's going to be, I do a KVL. So our KCL up here. Let's think of it this way. First, easy question should be how much current going through the resistor? 0. Why 0? I got a short parallel, right? So if I do a KVL around that loop, there's 0 volts across it, and there's 0 current through it. This guy must take the difference between that and that. So it's going to be I over 2. All right. We'll finish up with that example again on Friday.